Hi there, hope you're doing well today. We will be discussing and dealing with inverse. Inverse specifically of a function. You know all about inverse, you've been dealing with inverse for a long time. If I gave you an operation, let's say addition, you hopefully understand that the inverse operation would be subtraction. If I gave you multiplication, the inverse would be division, so on and so forth. It is the undoing of what is going on. It is also simply a switch of your x and your y values. We're going to be getting into these things a little bit later. It is a reflection over the line y equals x as far as a graph is concerned. First things first, let's deal with actually finding the inverse. So if you want to find the inverse, first thing we're going to do is we are going to switch our x and our y values, literally change places, and I know you don't see a y right there. And then we are going to solve for y. When we're dealing with x and y, we're talking about input and output, so a lot of times it's easier to replace this f of x with a y value. Y equals 2x plus 4. Now we are going to come through and we are going to actually solve that thing. We're going to do our switch, then we're going to solve it for y. So swap places, 2y plus 4. Now we need to get this y value all by itself, so subtract 4 divided by 2. There you go, we have solved for y, and that actually is our inverse, f inverse of x. Okay, we have found the inverse, so let me clean that up for us. F inverse of x equals x minus 4 over 2. That is our inverse right there. So we have our function right here, 2x plus 4, and we have the inverse, x minus 4 over 2. Okay, so what these are really kind of an easy way to think of it, function machines. So we could have f of x equals 2x plus 4 as one machine. We could have a secondary machine, pardon that little bump right there. Let's have our inverse. So f inverse of x equals x minus 4 over 2. Okay, so we have inputs and we have outputs coming out of these function machines right here. So if I were to want to graph these things, let's say, input and output. So we have x coming in and the function on x coming out. We would have x coming in here and the inverse function coming out. The operation on x. So when we put in an x value here to this, something's going to happen to it. First, it's going to be multiplied by 2, then we will be adding 4 to it. That is the function. When we put an x value in here, an input, first we will subtract 4, then we will be dividing by 2. Hopefully you're seeing how these undo each other. I have multiplication by 2 here, division by 2 here to undo it. I have addition of 4, the undo, the inverse, subtraction by 4. So let's say we start off with a value of, I don't know, how about 0? So if I were to take 0 and slide it in here into this machine, what will be coming out on the other end? Okay, so 0 times 2 is 0, plus 4 is 4. Fantastic. So when I put in the 0, I get out the 4. Well, if we run that through this function machine here, it should undo it. So if I were to start with my value of 4 and put it into the undo function, it should undo everything that's happening to 4, and we should end up with a value of 0. So let's put in 4 here and see what comes on out. Okay, so 4 minus 4 is 0. 0 over 2 is 0. Awesome, that was the undo function. How about a 1? If I slide in 1, 1 times 2 is 2, 2 plus 4 is 6. So if I were to run this 6 through the undo function, it should undo all these operations on 1. On that, and it should take me back to my value of 1. So let's slide in a 6 into the undo. Okay, so 6 minus 4 is 2. 2 over 2 is 1. Fantastic. The switching of these here. How about 2? We'll do one more. 2 times 2 is 2. 2 times 2 is 4. 4 plus 4 is 8. So if I stick the 8 in here into the undo, it should undo it, and we should end up with a value of 2. So let's input 8 into the inverse. So 8 minus 4 is 4. 4 over 2 is 2. Great, there we go. That is fantastic. That shows us that the inverse is actually just a switching of my x and my y values. So if you were to get a list of points like this, you could literally switch the 2 points, the x and the y value, and those would give you the set of points that represents the inverse. So let's look at this now graphically. I'm going to set up a nice little easy graph for us to take a peek at. There we go. We will be graphing some points right here. Let us start off with 0, 4, 0, and I will do this in purple, my function. So 0, 4, 1, 6, 2, 8. Okay, so we've got a slope of 2, so I could continue that slope for as long as we wanted right there. Awesome. Okay, let's get a secondary one. Let's deal now with my inverse. I will make that maroon, a different color, even though they look kind of similar. Sorry about that. So 4, 0, 6, 1, 8, 2. All right. So a slope of up 1 over 2, a slope of positive 1/2, down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2, da 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 da, on and on and on. There we go. Those are our 2 graphs. This would be the function, f of x. This would be the inverse, f inverse of x right there. Huh. All right. Now, if we have this wonderful, wonderful line, it is one you should be familiar with. This line right here, kind of that 45 degree, that is y equals x. Whatever x is, y is. There you are. Now if you look at these 2 graphs, the inverse is a reflection over y equals x of the original function. These 2 mirror each other. They essentially undo each other to take us back to that. Switching of x and y. The reflection over x equals y. If you would like to find the inverse, swap your x and your y and solve for y. All right, let's take a look at another example. There's something else we need to discuss right here. Let's say we have another function. B of x equals x squared plus 1. Let's find the inverse of this. So find the inverse, B inverse of x. Okay, if you want to find that, first thing that we need to do is we need to swap our x and our y values. So remember that is very similar, the output, that is similar to my y value. So I would have y equals x squared plus 1. We're going to swap the x and the y. So I will get x equals y squared plus 1. Subtract 1, x minus 1 equals y squared. Y squared, all right. The way I'm going to undo that would be to take the square root of both sides. So I'd get the square root of x minus 1 equals y. Now that would be our inverse. So B inverse of x equals x minus 1 root. There you go. There's our inverse. Now, mathematically, this would need to be the positive and negative root for this to hold. Think of your quadratic formula when you were dealing with that right there. That's kind of another lesson for a different time. So, this could be expressed in another way, possibly for the ease of graphing on a computer. It could be x minus 1 with an exponent of 1/2. Those are all the same right there. All right, so we can take a look at some of this stuff right here. Let's say we wanted to graph these 2. Let's get a b of x equals, what do we have, x squared plus 1. I'll switch my color up. Let's do b inverse of x equals root x minus 1. So I'm going to show you a couple things here about some constraints and some limitations. So input, output. Let's say we input a 0. Well, 0 squared plus 1 is 1. There's my first point. Let's say we put in a value of 1. 1 squared is 1. 1 plus 1 is 2. How about an input of 2? 2 squared is 4. 4 plus 1 is 5. Let's say we input 3. 3 squared is 9. 9 plus 1 is 10. All right, so for my inverse over here, you can just look at this set of points and you could literally flip-flop them. 1, 0, 2, 1, 5, 2, and 10, 3, because it is a switching of your x and your y. 1, 0, 2, 1, 5, 2, and 10, 3. Now this does hold true. Those work out. If you put in 1, 1 minus 1 is 0. Root of 0 is 0. If you put in 2, 2 minus 1 is 1. Root 1 is 1. 5, 5 minus 1 is 4. Root 4 is 2. So those points do actually hold up right there. So I want to take a look at our graphical representation of this right now. Where should I start that? There we go. All right, first let's look at our function. So I have 0, 1. I have 1, 2. I have 2, 5. I have 3, 10. 5, 6, 7, 8, 9, 10. There we go. Well, what about my negative range over here? Definitely goes into that negative range, but I just want to look at this positive range for 1 second. Okay, you know, it is a parabola, it is squared, so we would have our symmetry on the other end, on the other side of this. So, if we were to continue on, the other part of my parabola would look like that. Well, it is a reflection, and we are finding the inverse. Okay, so let's now take a look at the graph of my inverse. I get 1, 0, 2, 1, 5, 2, and 10, 3. There we go. Now looking at that, we could have some symmetry with this thing as well. It is a parabola. So that would actually be the other half if we came through and we understood and we actually applied the positive and negative root here. Okay, I did not actually do that, but mathematically if you wanted to get the other half of this right here, we would need to take the positive and negative root. Interesting. So now I want you to think about that. We have a function. If it is a function, it means that it passes the vertical line test. So my original parabola right here up top, including the second half, would pass the vertical line test. So b of x is a function. Yes, it is. And this half right here is actually part of the parabola, even though it is dashed. It should be filled in. Well, look at the inverse. It is a reflection. So if I were to take my parabola and reflect it, I'm going to end up with this parabola right here. Well, if this half is part of my original parabola, this half would need to be part of my reflected parabola. Well, I'm saying that this is also a function. And if you look at this red parabola right here, the inverse, it is the inverse function. For the inverse function to truly be a function, it would need to also pass the vertical line test. And if you were to look at this with this lower half, that would fail the vertical line test. This is not a function here. That is why we cannot be using this other half of my parabola. It cannot exist. We would need to constrain this. B of x could only work and have an inverse if x is greater than or equal to 0, only for this other half of the parabola. So ignore this dashed part right here, only look at the solids. Now the reflection over the line x equals y holds true, and the function and its inverse are both truly functions. You can't call it a function if it's not a function. So, to put this into words, if b of x has an inverse, the inverse, b inverse, of x needs to be a function. So we constrain b of x to just have x values that are greater than or equal to 0 for this particular graph, because that is our direction change, the vertex right there where it switches spots, switches directions. I hope that makes sense. I'm going to get into some proving of inverses and a few other things here in a few moments on a different video. Thank you very much.